Hello, everyone. This is Group 1 presenting digital transmission in free space through a high-powered laser. Our mentors being Dr. Wei and Dr. Carr, our committee being Dr. Sahawin and Dr. Maddox and Dr. Eikenberry. Meet our team. Alexander Simmons, a photonics engineer. Curtis Kane, an electrical engineer. Ivan Huang, a photonics engineer. And Monica Castro-Suarez, a computer engineer.
My name is Ivan, and for the background motivation, the basis of our project is on long distance communications, which is possible thanks to the invention of the telegraph in the 19th century and the laser and fiber optic cable in the 20th century. As we're going to send digital signals, which are composed of ones and zeros, a laser can be modulated to send these signals as pulses. Laser communications already exist, but mostly with satellite-based communications. And this project aims to demonstrate the possibility of free space laser communications on Earth for transmission of sensitive data. As for goals and objectives, our basic goals are to convert digital signals into optical pulses by developing a system for coded modulation and purchasing a laser with transistor logic circuitry, and maximizing signal reception by developing an efficient optical system and selecting a photodiode that can accept 980 nanometers. The advanced goals are real-time decoding through developing a microcontroller system and integrating AI machine learning capabilities, and also optimizing signal transmission through simulating possible optical layouts with the best results and finding better lenses and mirrors. As for stretch goals, we would like to develop this project for off-grid emergency use by introducing bidirectionality and shrinking the system into a smaller portable form factor, and megabit transmissions by switching to a low frequency laser and integrating electro-optical components to increase the power of the laser and allow it to carry more data. For engineering requirements, we would like the decoding accuracy to be 95% accurate to ensure reliable signal interpretation, a data transfer rate between 50 kilobytes per second to 1 megabit per second for flexibility and signal speed and transmission. Um, we would like the system to consume at 5 watts max, 5 watts power max for low power operation, a transmission distance between 20 to 50 feet for optimal signal integrity. Power efficiency, 85% of the time with 5% voltage ripple max for portability and long operational life. Interference immunity greater than or equal to 40 decibels for elimination of electromagnetic interference, and a bit error rate of at least uh, less than 10 to the negative 5.
Hello, my name is Alexander Simmons, and this is a brief overview of the optical parts used in the project. We have our laser at 980 nanometers, our beam expander using a positive meniscus lens, a focusing lens, photodiode, and a bandpass filter. We will go into more details for each component and design calculations for them in further slides. For our laser, we compare different laser types with parameters such as pulse duration, repetition rate, and we went with the TTL modulated laser diode because of its simplicity, affordability, adequate modulation speeds for free space optics, and compatibility with beam shaping optics at 980 nanometers. The higher end lasers such as femtosecond fiber were ruled out due to excessive cost and complexity not needed for mid-range data links. The design calculation on the right shows power density for the TTL laser at 1 kilometer, showing it produces more than enough power per centimeter squared for our purposes. For the photodiode comparison, we compared different parameters such as responsivity, bandwidth, and internal gain over PN diode and PIN and avalanche photodiode. We chose the PIN photodiode due to its happy medium responsivity to cost ratio, of 0.6 amps per watt at 980 nanometers, and its 30 megahertz bandwidth supporting pulse modulation, its lower dark current and noise, and its adequate speed for TTL modulated laser pulses at 100 kilohertz. The design calculation on the right shows our photocurrent signal with incident power and our signal to noise ratio with theoretical amplifier noise current. For our different expanding lenses, we compared different parameters such as beam expansion quality, various different aberrations, and transmission efficiency. We went with the positive meniscus lens because it had a lower divergence when compared to other lenses, the meniscus ones being 0.8 millirads versus greater than 1 millirad. Its spherical aberration was more manageable. It had a higher transmission and compact design when compared to others, and had a less complexity and cost than the achromatic doublets. For the design calculation on the right, we show the beam divergence and the beam size with and without expansion, showing the different beam sizes over distances with and without the beam expander. For our focusing lens, we compared different parameters such as spot size, aberration correction, focal length, and numerical aperture. And we went with the aspheric lens because of its tighter focus, being less than 10 micrometers, matched the photodiode aperture and the distance we want between it. The numerical aperture of 0.55 enabled strong convergence from wide input beams. Its low aberration improved our accuracy and had an AR coating optimized for 980 nanometers. The achromatic lens we excluded due to unnecessary chromatic correction and added bulk cost. For our optical filter, we compared long, short, and bandpass filters with parameters such as central allowed wavelength and transmission efficiency. We went with the bandpass filter because it provided a 99% transmission at the laser wavelength. It blocked unwanted ambient light across visible and infrared, and enhanced signal-to-noise ratio under outdoor lighting conditions, and is more selective and efficient than short pass or long pass alternatives. For our optical system diagram, beginning on the left, we have our transmitter, which uses a microcontroller that modulates a 980 nanometer laser diode using TTL signals. The beam is then expanded using a meniscus lens to reduce divergence and maintain culmination over longer distances. We then hit our horizontal and vertical alignment mirrors for adjustment, and after traveling through free space of roughly 1 kilometer, the beam passes through a 980 nanometer bandpass filter to block ambient light. It then is focused through a focusing lens that concentrates the beam onto a fine adjustment mirror to align with our photodiode, which then converts the optical signal back into an electrical signal for decoding and display. For our beam propagation challenges, atmospheric effects of free space optics, the main takeaways are the key trade-offs of smaller beam diameters, increasing divergence and reducing range efficiency, and without the culmination lens, the beam will spread over distances, which reduces the intensity at the receiver. The long-range impacts over longer distances, 1 kilometer to 2 kilometers, are higher alignment sensitivity, reduced signal-to-noise ratio under turbulence, and limited beam range without optical correction. This is a brief example of atmospheric effect on beam divergence. You can see the wider cone of divergence seen at the left-hand side, expanding through the atmospheric turbulence in the lens system, and you can see how the arrows through the lens system are being diverted by these effects through the entire system. And these effects can be anything from heat, wind, or any sort of turbulence. These effects make it more difficult for the smaller beams to reach its target accurately, even through precise alignment, and it causes the beam to wander, essentially. For larger beams, it is less affected, but it is instead resulting in a speckle pattern in the beam itself. To mitigate the constraints above atmospheric effects or beam divergence, the project implements a beam expander at the transmitter and a focusing lens at the receiver. For the beam expander to reduce divergence, we increase the initial diameter of the beam via the beam expander and culmination lens system. This system then reduces our divergence angle, preserves our beam intensity, reduces beam spread, and ensures adequate optical power reaching our detector. For the focusing lens at the detector, it then catches the expanded beam, focuses it into our fine adjustment mirror that we can then adjust into our photodiode head or detector, and it compensates for small adjustments error from its atmospheric effects since it's not a smaller beam going through our transmission distance. For our speckle pattern in large and small beams, The overall is smaller beam sizes, the speckle pattern is densest and easier to average with our photodiode. For our larger beam size, the speckle pattern is larger or expanded and more difficult to average with a single detector head because of hot spots in the speckle grain. For our design solution, the beam expander reduces divergence from atmospheric effects by making the beam size larger. The focusing lens then reconcentrates the expanded beam so the photodiode can average the incoming data. For our results, it should improve our signal-to-noise ratio, reduce our alignment sensitivity and beam divergence, and make it more easy and more reliable for averaging of our detection of our beam by the photodiode. This is a brief example slide showing the speckle pattern of expanded beam, and in section B you can see the hot spots in our beam in the beam itself. This is our main optical calculations and software used to test or evaluate our optical systems, which we will talk about more in the further slides.
Hello, everyone. My name is Monica. For software comparison, I am using the MSP430G553 for testing and to implement onto our microcontroller when we build our PCB. I tried 3 different softwares, which being Code Composer, Arduino IDE, and MicroPython, and chose Arduino IDE due to I am able to use C language as well as it is user-friendly. Though its performance is medium compared to Code Composer, it still works well with me and what I needed to do.
Hello, this is Curtis Kane and this is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller and its output is then sent to the LCD to be displayed. Using Fusion 360, we developed a detailed 3D CAD model of the physical system, including the PCB container, condensed component layout, and light optical mounting. 2 additional views are zoomed in to show how components like the PCB and photodiode are positioned for alignment. Creating this model helped guide physical prototyping by verifying mechanical fit, optical paths, and wire routing in advance. We chose the ATmega 328P as our microcontroller for our main PCB because it has a robust community, wide Arduino compatibility, and sufficient specs for our task. It features 32 kilobytes of flash and 2 kilobytes of RAM, allowing us to buffer and process binary signals fast and effectively. Its 10-bit ADC is perfectly adequate for reading the photodiode amplifier output and transferring it to our LCD display. Most importantly, its 1.8 to 5.5 volt operating range gave us flexibility with the voltage regulation. This schematic shows how we wired the ATmega 328P to support faster laser modulation, photodiode input, and LCD output. The inclusion of programming headers to reprogram the MCU aids in making the PCB easier to troubleshoot in the future, as we can now adjust the code on the fly if any parameters were to be changed. Power connections to both 5 volt and 3.3 volt rails are also included as part of the MCU design to power both the LCD header and the MCU itself. This clean layout will allow us to easily troubleshoot and test each stage of the system. The OPA 381 was our amplifier of choice for the photodiode to transimpedance amplifier signal chain. Since it is optimized for transimpedance applications, it has a very low input bias current of only 3 picoamps on average. Its 18 MHz gain bandwidth makes it ideal for detecting fast optical pulses with minimal signal degradation. And at around $1.80 per unit, it offers strong performance without breaking the budget. Here you can see our transimpedance amplifier circuit using the OPA 381. Instead of a single hardwired photodiode, we opted for a header to bring more adaptability to our overall circuit design. This header will allow us to swap the photodiode easily in direct response to any dramatic changes in wavelength of our input laser. With the photodiode wired into the header, the photodiode's current will enter the inverting input, and the output will provide a clean voltage signal proportional to the light intensity. To power the system reliably, we implemented two boost regulators on daughter boards. We used the TPS 61322-1A to generate 3.3 volts for the amplifier, and the TPS 6132222A for the 5 volts to power the microcontroller and LCD. These regulators helped ensure stable performance even as battery voltage dropped, which is critical during long testing sessions. This slide brings it all together, showing the complete system schematic. You can see the flow of signals from the photodiode and amplifier into the microcontroller, which then sends data to the LCD. It also shows programming pins and extra LEDs for debugging, an important feature that will save us time during development.
This is our software design flowchart. This system enables wireless data transmission using a high-power laser. Input data is encoded into binary by light microcontroller and sent as light pulses via optical transmitter. A photodiode receiver captures the signal and converts it back into electrical data. A decoder reconstructs the original message, which is then displayed on an LCD. The software manages encoding, timing, error handling, and display formatting for reliable real-time communication. This is our general overview of the software design that we are using.
As we began testing, we encountered two major issues. First, our initial microcontroller, the MSP430, was not giving stable results. Switching to the ATmega328 solved this brief problem and even simplified our code. Second, we initially overestimated the photodiode's output current, which led to overamplification and invalid readings. This was swiftly fixed by retesting components and recalculating our results. These issues helped us better understand the importance of theoretical verification and proper component matching. Our current setup is now functioning with accurate readings and a stable digital output.
Prototype and testing, the software section. In this demo, I tested the LCD and LED control logic before the final hardware was available. I used a MSP430 FR6989. Due to its built-in LCD, low power use, and compatibility with Code Composer. The system initialized GPIO and LCD settings, displays the number 430 using a 7-segment lookup, and controls the red LED on pin 1.0. Future versions will allow users to input words like Hello World using each character on LCD along with its binary form. While the LED blinks on and off based on each binary bit, this serves as proof of concept for display and I/O logic ahead of full integration in senior design 2. Prototype and testing, software, problems encountered, solutions developed. One of the initial challenges during preliminary testing was selecting an appropriate MSP430 development board. The decision was between the MSP430-6989 and the MSP430G2553. The MSP430FR6989 was chosen for prototyping due to the integrated LCD module, which enabled convenient testing and visualization of output without the need of an external components. However, the final implementation will transition to the MSP430G2553, aligning with microcontrollers used on the custom PCB. The developed code will be ported accordingly to ensure compatibility with the target hardware.
The photodiode that we will be testing is the FDS100 silicon photodiode from Thor Labs. The critical aspect of the photodiode that we will be measuring is the responsivity, as well determine the amount of current generated per watt at a given wavelength. From Thorlab's specification sheet, the responsivity of the photodiode is 0.6 amps per watt at 900 nanometers, which is the wavelength of our laser diode. Since we don't have the laser diode yet, we have yet to measure its actual responsivity. As for our optical system, we used Zmax to model the system. On the left is our table of parameters that have been optimized so that Zmax can create the most efficient optical system. And on the right is the 3D diagram of the optical system with the optimized parameters. For modeling the bit error rate, we used code generated by Gemini AI to model the BER for the BPSK at the bit error rate of 5e to the negative 4, 2e to the negative 4, 1e to the negative 4, and 1e to the negative 5. And e just represents base 10. And this plot over here shows that a higher signal to noise ratio, which is measured in decibels, is correlated with the lower bit error rate. And this will be the case as the number of bits transmitted increases. Once we have the laser diode, we can measure the actual bit error rate with an oscilloscope. And the importance of this plot is that we must reduce the amount of noise from physical obstacles and electrical interference as much as possible so our signals don't get distorted. For our work distribution, for the primary roles, Curtis will be doing PCB design, Monica will be doing embedded coding and software design, Alexander will be doing optical design, and I will be doing the optoelectronics testing. For the secondary roles, Curtis will be doing 3D modeling, Monica will be doing website design and management, Alexander will be doing laser calibration and alignment, and I will be doing optical simulations. And this is our budgeting list with our laser diode with the transistor logic capabilities, the photodiode, mirrors which come in a set of 3, lenses which come in a set of 6, focusing lens, optical filter, LCD screens, transimpedance amplifier, microcontrollers, PCBs, and power source, which all come down to a total of $245.04.
Progress and plan for completion. To build a strong team dynamic and set the project up for success, several key meetings and events were held early on. These meetings focused on discussing project goals, aligning expectations, and laying out a clear direction. This helped provide a solid foundation for the work ahead and ensured everyone was on the same page from the start. This is the progress chart for senior design 2. We have the PCB schematic, the optical design, embedded software, prototype construction, the prototype testing, and the calculations. The green signifies the completed state, as well as the blue signifies that we are in progress, and the orange signifies that we are not completed at the moment, but we are working towards it. This is the plan for completion. So we have each week that we have something that we have to turn in. We like to work ahead of time just so we know what things are due. And yeah, does anyone have any questions, any concerns, anything that you want to throw at us and see what we can do? Please feel free and ask us. Thank you.